Welcome to topic 4101, Urban Flood Resilience. In this session, we treat flooding as an environmental planning challenge, not only an engineering problem. Resilience is about how a city anticipates, absorbs, and recovers from flood events while continuing to provide essential services, transport, housing, health, water, energy, and public space. We will connect sustainable development principles to concrete planning decisions, where we allow development, how we shape landscapes, and how we combine green and gray infrastructure. As you listen, keep a planner's perspective in mind. You may not be designing pipes or running models day to day, but you do set the rules, priorities, and spatial strategies that determine what risks a city creates or avoids. By the end, you should be able to explain key concepts, recognize the main tools, and discuss how global frameworks and ethics shape resilient, equitable outcomes. Here is the roadmap. We begin with why urban flood resilience matters and how flood risk forms, from rainfall to impacts. Then we connect ecological principles and ecosystem services to the spatial organization of cities, because land cover, soil, and urban forms strongly influence runoff, flow paths, and who is exposed. Next, we review the data foundations and the modeling toolbox, including how resolution and scale choices affect what you can confidently conclude. From there, we look at how future climate and land use change alter assumptions, and we compare nature-based, gray, and hybrid infrastructure strategies. We then shift from technical options to planning practice, policies, zoning, scenario testing, and robust decision-making. Finally, we ground the concepts with two best cases and close with practical takeaways you can use in planning work, studio projects, and interdisciplinary collaboration. As we go, notice the recurring theme. Decisions about land use and public space can either amplify runoff and exposure, or provide room for water and safer development patterns. These are the learning objectives for topic 4101, aligned to the course learning outcomes. First, you should be able to define basic concepts and principles of sustainable development and environmental planning, and explain why they matter for flood resilience. Second, you should describe how ecological principles and ecosystem functions relate to spatial organization and urban environments, especially how landscapes provide regulating services like water storage and flow attenuation. Third, you should explain, at a general level, how climate adaptation and infrastructure planning support environmental sustainability, including the role of modeling and scenario thinking. Fourth, you should identify key global and regional frameworks that guide environmental planning practice, such as the Sustainable Development Goals, the Sendai Framework, and major flood risk policy instruments. Finally, you should show awareness of ethical responsibility and teamwork, because resilience planning always involves trade-offs, uncertainty, and diverse stakeholders. We will revisit these outcomes at the end for self-check. Briefly, why does urban flood resilience matter? Cities concentrate people, assets, and critical infrastructure, so even a short-duration flood can cascade into transport disruption, business interruption, health risks, and long recovery periods. Importantly, urban flood risk is not driven by a single cause. It emerges from the interaction of changing rainfall patterns, urbanization and impervious surfaces, altered drainage pathways, and the limits of existing infrastructure capacity. From an environmental planning standpoint, resilience means shaping the city so that flood impacts are reduced and recovery is fair. That includes where development happens, how density is managed, how open space functions, and how services are protected. A resilient strategy also recognizes that different neighborhoods experience different levels of exposure and vulnerability. So the goal is not just bounce back, but to reduce risk over time, avoid locking in harm, and improve the ability of all residents, especially the most vulnerable, to cope with future events. This slide frames flood risk as a chain rather than a single moment. Start with a hazard, rainfall intensity and duration, then consider how the catchment and the city convert rainfall into runoff. Runoff becomes surface flow. Flow interacts with drainage and topography, and only then does water reach people, buildings, and services. Impacts depend not only on water depth or velocity, but also on what is located in the flow path and how prepared the community and institutions are. The planning implication is powerful. You can intervene at multiple points. Upstream and at source measures reduce runoff. Spatial planning can reduce exposure by steering critical functions away from flood-prone areas or by designing safe overflow routes. Vulnerability can be reduced through building standards, warnings, and social support systems. In practice, the strongest approaches combine hazard reduction, exposure management, and vulnerability reduction, because no single measure is sufficient under real-world uncertainty. Topic 4101 also requires connecting ecological principles to urban environments. In flood resilience terms, ecology is not decoration, it is functional infrastructure. Natural systems store water in soils and vegetation, slow down overland flow through roughness and root structure, and enhance infiltration where soils and groundwater conditions allow. Wetlands, floodplains, parks, and permeable corridors can act as buffers that reduce peak flows and provide space for water during extreme events. These processes are often described through ecosystem services. For flooding, the key services are regulating services, water retention, filtration, and flow moderation, but there are co-benefits: biodiversity, cooling, recreation, and improved public space. For environmental planners, the point is to design spatial patterns that protect and restore these functions. That means thinking in systems, catchments, green networks, and urban form working together, and avoiding fragmented, green patches that look good but do little for hydrological performance. Spatial organization is where environmental planning most directly shapes flood outcomes. Exposure and vulnerability are not random. They are produced by land use decisions, housing markets, infrastructure siting, and historical planning choices. A flood map may show a hazard zone, but the real question is, what did we put in that zone, and who lives or works there? On this slide, consider how the same rainfall can create very different impacts depending on urban form. Dense impervious surfaces generate more runoff. Barriers like road embankments can redirect flow and create unexpected ponding. Informal or low-quality housing may be more vulnerable to damage. Critical facilities, hospitals, power substations, transit hubs, create systemic risk if they are exposed. Planning tools, zoning, setbacks, open space networks, and development control can reduce exposure. Social policy and inclusive engagement can reduce vulnerability. Together, they translate ecological understanding into spatial strategies that improve resilience without relying solely on hard infrastructure upgrades. Good decisions depend on good data. Urban flood assessment typically draws on topography, land cover, soils, drainage networks, rainfall records, and information on people and assets. In practice, you often work with imperfect, heterogeneous datasets. Digital elevation models can miss small features like curbs, walls, and micro-depressions, yet those features strongly affect flow routing. Land use layers may be outdated or too coarse to represent recent development. Social data can be sensitive and unevenly available. The key planning lesson is to treat data as an uncertainty to manage, not as a reason to avoid analysis. Start by clarifying the decision you need to support, screening hotspots, prioritizing interventions, or evaluating alternatives, and then match the data effort to that purpose. Document assumptions, check consistency across layers, and look for decision-relevant accuracy rather than perfect precision. Where data are weak, combine quantitative layers with local knowledge, site visits, and stakeholder input to avoid blind spots. Urban flood modeling spans a toolbox, from simple screening methods to detailed hydrodynamic simulations. Conceptually, models translate rainfall and catchment conditions into runoff and water movement, and then into metrics such as inundation depth, extent, duration, or potential damages. Different models answer different planning questions. At one end, you have rapid methods, index-based screening, simplified runoff calculations, or GIS-based flow accumulation, to identify likely hotspots and support early planning discussions. At the other end, hydrodynamic models can represent surface flow and drainage interactions, producing detailed maps that are useful for design and evaluation. Between these extremes are coupled approaches that link land use change scenarios with hydraulic models, or combine 1D drainage representation with 2D surface routing. For planners, the most important skill is model literacy, knowing what a model can and cannot claim. Ask, what processes are represented? What data does it require? What is the uncertainty? And does the model output actually support the decision you are making? Resolution and scale choices are central to model credibility. A model with very fine spatial resolution can represent more detail, but it demands higher quality input data and more computation. If the elevation data, drainage inventory, or rainfall inputs are uncertain, making the grid smaller does not automatically make the results more trustworthy. Conversely, a coarse model may miss local flow paths and underrepresent small but critical flooding problems, such as ponding at underpasses or near blocked inlets. A practical approach is to choose resolution based on the decision context. For city-wide prioritization, a coarser approach may be appropriate if it reliably identifies relative hotspots. For evaluating a specific neighborhood intervention, finer resolution and targeted data collection may be justified. Always communicate scale limitations. Outputs are not truth, they are decision aids. Finally, remember that scale also includes time. Short intense storms require different temporal resolution than longer events. Matching spatial and temporal scale to the planning question is a hallmark of defensible analysis. Flood risk is dynamic because both the hazard and the city are changing. Climate change introduces shifts in rainfall intensity patterns and increases uncertainty around design assumptions that were built on historical records. At the same time, land use change, densification, expansion into peri-urban areas, loss of vegetation, and increased imperviousness often increases runoff and reduces natural storage. For environmental planning, this means avoiding one scenario thinking. Instead, use scenario analysis. Explore multiple plausible futures for climate, development, and policy. The goal is not to predict the exact future, but to identify strategies that work reasonably well across a range of conditions. This is where adaptive pathways become valuable. Implement near-term actions that provide benefits now, while keeping options open to adjust as new information emerges. In practice, this mindset changes how you interpret model outputs. Rather than seeking a single, best, design storm, you test sensitivity, identify tipping points, and prioritize flexibility, especially for investments with long lifetimes like land use patterns and major infrastructure. Blue-green infrastructure and nature-based solutions are central tools in sustainable flood resilience. Blue-green interventions include parks designed for temporary storage, green corridors that provide conveyance routes, green roofs that reduce and delay runoff, rain gardens and bioswales that capture water locally, and restored floodplains or wetlands where space allows. The shared idea is to work with natural processes, storage, infiltration, evapotranspiration, while providing additional urban benefits. From a planning perspective, the strength of blue-green infrastructure is its multifunctionality. It can contribute to flood mitigation and simultaneously improve biodiversity, heat comfort, air quality, and the quality of public space. However, it is not magic. Performance depends on soil conditions, maintenance, design capacity, and where interventions are placed within the catchment. Equity matters too. Benefits should not be concentrated only in high-income areas. A defensible planning strategy treats nature-based solutions as part of a system, integrated with zoning, street design, and drainage upgrades, and evaluated under the same rigorous scenario testing as gray infrastructure. Gray infrastructure refers to engineered drainage and flood control systems, pipes, culverts, detention tanks, pumping stations, flood walls, and channels. These measures can be effective for specific design conditions, especially where dense urban form limits space for storage. But gray-only strategies face limits under changing climate extremes, aging assets, and high retrofit costs, and they can shift risk downstream if not catchment aware. That is why many cities move toward hybrid strategies, combining gray capacity improvements with blue-green measures and spatial planning. Targeted pipe upgrades can be paired with upstream retention, permeable surface policies, and designated safe exceed-dance pathways in streets. For planners, the decision is rarely green versus gray. It is how to assemble a portfolio of measures that reduces risk, delivers co-benefits, and remains credible under uncertainty. Urban planning policies and zoning translate flood risk knowledge into enforceable decisions. This includes steering new development away from high-risk areas, limiting vulnerable land uses in flood-prone zones, requiring elevation or flood-proofing, and protecting open space networks that provide storage and safe flow routes. Planning also influences risk indirectly through density, street layout, and the location of critical facilities. Risk-informed planning uses flood assessments to guide where growth occurs and what conditions apply to approvals. Policies can require site-level stormwater controls, cap imperviousness, or mandate green infrastructure integration. Street design can also incorporate multi-use spaces that safely accommodate occasional flooding. Implementation requires coordination across land use plans, infrastructure budgets, and emergency management, plus periodic updates as risk and data evolve. Scenario testing and robust decision-making help planners act under uncertainty. Rather than asking, "What is the single best solution for one forecast?" robust approaches ask, "Which strategies perform acceptably across many plausible futures?" This matters for flooding because rainfall extremes, urban growth, and behavioral responses are uncertain. In practice, you define performance metrics, such as reduced inundation in critical corridors or protection of essential facilities, and test candidate strategies across multiple scenarios. Strategies that consistently meet thresholds are preferred. If none performs well everywhere, you design adaptive pathways, sequences of actions that can be adjusted over time, with clear triggers for when to escalate. Robust methods support transparent trade-offs. They reduce overconfidence in a single model run and help justify decisions to stakeholders. They also allow non-technical criteria, equity, co-benefits, feasibility, to be assessed alongside hydrological performance. Frameworks guide sustainable planning by turning broad goals into responsibilities and evaluation criteria. At the global level, the Sustainable Development Goals, especially 11 Sudanese pounds on sustainable cities, emphasize inclusive, safe, resilient, and sustainable urbanization. The Sendai Framework for Disaster Risk Reduction similarly highlights understanding risk, strengthening governance, investing in resilience, and improving preparedness and recovery. At the regional level, policy instruments such as the EU Floods Directive formalize processes, risk assessment, hazard and risk mapping, and flood risk management planning, typically on a cycle with updates. National adaptation plans and disaster management strategies then translate these principles into country-specific priorities. Finally, local comprehensive plans, zoning codes, and infrastructure programs operationalize them on the ground. For learners, the message is that flood resilience is not optional or ad hoc. It is embedded in governance frameworks. Knowing these frameworks helps planners justify interventions, coordinate across departments, and design plans that are defensible under public scrutiny and regulatory review. Ethics, equity, and teamwork are not soft add-ons. They determine whether resilience planning is legitimate and effective. Flood risk often falls disproportionately on low-income households, informal settlements, and communities with less political voice. If planning decisions ignore these patterns, interventions can unintentionally reinforce inequality by protecting high-value districts first, displacing vulnerable residents, or creating green upgrades that drive gentrification. Ethical responsibility in environmental planning means making distributional impacts visible and addressing them explicitly. That includes inclusive engagement, transparent criteria for prioritization, and attention to accessibility and co-benefits. It also means communicating uncertainty honestly, avoiding false precision, and acknowledging that technical models do not replace public values. Teamwork is essential because flood resilience crosses disciplines and agencies. Planners, engineers, ecologists, public health officials, emergency managers, and community groups. Effective teams establish shared problem definitions, agree on data and assumptions, and use clear decision processes. As you move into practice, aim to be a translator between technical evidence and planning choices, keeping fairness and long-term sustainability at the center. Best Case 1 illustrates how scenario-based modeling can support concrete planning actions. In the Zhengzhou case, a coupled hydrodynamic modeling approach was used to explore inundation patterns under multiple rainfall scenarios and urban conditions. The value for planners is not just a map, it is the prioritization logic that maps enable. By consistently identifying recurring high-risk zones, often near low-lying areas, river-adjacent corridors, or constrained drainage pathways, the analysis helps target where interventions matter most. Planning translation can take several forms. First, the city can focus monitoring and maintenance on key bottlenecks. Second, spatial controls can limit new vulnerable development in hotspots. Third, infrastructure upgrades can be staged, beginning with locations where multiple scenarios converge on risk. Fourth, emergency planning can pre-designate safe routes and shelter locations based on modeled flow paths. The broader lesson is that models are most useful when they are scenario-based, linked to decisions, and paired with clear communication about assumptions and uncertainty. Best Case 2 highlights adaptive planning under uncertainty. using Melbourne as an example of evaluating multiple combinations of climate futures, development pathways, and adaptation options. The key insight is that fixed, one-off investments can perform poorly if the future diverges from the assumed scenario. Adaptive strategies, implemented in stages, with monitoring and triggers, can maintain acceptable performance across a wider range of conditions. In this type of framework, the city tests policy instruments alongside infrastructure measures. Limiting exposure through land use policy can be highly cost-effective because it prevents new risk from being created, while incremental drainage or storage upgrades can be timed to match observed changes. For environmental planners, the lesson is to treat resilience as a long-term governance process. Act now, learn, and keep options open. To close, the key message of topic 4101 is integration. Urban flood resilience improves when sustainable development principles, ecological systems, spatial planning, infrastructure choices, and governance frameworks are treated as one connected field of environmental planning. Conceptually, remember the risk chain: hazard, runoff, flow, exposure, vulnerability, and recovery. Practically, remember the portfolio: blue-green measures, gray capacity, hybrid strategies, and risk-informed land use policy. From an evidence standpoint, use models and data as decision support, not as unquestionable truth. Choose tools that match the scale and purpose, be explicit about uncertainty, and test strategies across scenarios. From a governance standpoint, use frameworks like 11 Sudanese pounds, the Sendai framework, and flood risk policy processes to align local plans with broader responsibilities. As you apply these ideas, start small and be explicit. Define your decision question, list assumptions, and identify who benefits and who bears risk. In studio or professional settings, document alternatives, compare them with clear criteria, and communicate trade-offs in plain language. Finally, keep ethics and teamwork central. Resilience that protects only some neighborhoods is not sustainable. The goal is planning that reduces risk over time, supports environmental quality, and distributes benefits fairly.